Hello, good morning. I am Professor Lee. Today we'll discuss astronomy. We begin with galaxies orbiting the mass centers. Lesson 1. Search for dark energy/matter. Lesson 1. Is it true that the farther away galaxies are, the faster they recede? Does dark energy matter accelerate the expansion of the universe? Astrophysicists read, measured, and calculated stars and galaxies' movements by observing the universe. They found farther galaxies had larger redshifts and receded faster. Their conclusion was that galaxies keep speeding up. Their reason is dark energy/matter. Dark energy/matter accelerates the universe's expansion. Let's start with an exploration of dark energy/matter. First, we must decide on the search locations. Let's find the locations by trial and error on paper. We use an ellipse as a two-dimensional universe. We divide it into three rings, A, B, and C. Figure 1a, we have four cases. 1. The dark energy is in ring A. Results: expansion in ring A greater than expansion in ring B greater than expansion in ring C. 2. The dark energy is in ring B. Results: expansion in ring B greater than expansion in ring C, and ring A will contract. 3. The dark energy is in ring C. Results: ring C will expand, and ring B will contract more than ring A. 4. We cross-cut the oval into four parts, 1, 2, 3, and 4. The DE/M is in part 1. Results: part 1 will expand and parts 2 and 3 will contract more than part 4. It will have similar results for DE/M in all the other parts. The universe looks like figure 1c, not figure 1b, which is affected by dark energy toward matter. All the results disagreed with our observations. There's either no dark energy matter or it must be uniformly scattered. If it's evenly scattered, it should evenly distribute within our solar system and inside the Earth's orbit. If the dark energy matter is located outside the solar system, with its force much larger than the Sun's, Earth would be pushed into the Sun in no time. If it is located between the Sun and Earth, general relativity predicts that light's path will bend in the gravitational field. Repulsive force will bend it in the opposite direction. With our current technologies, it should be detected. There is a possibility that some satellites could be affected by dark energy matter curvature fields. We find dark energy/matter nowhere. Is dark energy matter another ether? Lesson 2. Galaxies orbit mass gravity centers. An astronomer, Paul, lives on a planet 400 million light-years away. He observed and measured two stars, Xena and Human, for 4 years. He analyzed and calculated the information. He had the following results. His measurements showed that x1 less than x2 less than x3 less than x4, x1, x2, x3, and x4 were the increased distances for years 1, 2, 3, and 4 of star Xena, respectively. Vx1 less than Vx2 less than Vx3 less than Vx4 eq1. Similarly, he found y1 less than y2, y2 less than y3, y3 less than y4, and y4 less than y1, y2, y3, and y4 were the increased distances for years 1, 2, 3, and 4 of the star Human, respectively. Vi1 less than Vi2 less than Vi3 less than Vi4. Equation 2. Equation 1 and Equation 2 show that velocity increases year after year. Vy1 less than Vy2 less than Vy3 less than Vy4. Equation 3. Equation 3 shows that the farther the star was, the faster its velocity. At the same time, Paul's colleague Peter used Doppler radar to read the velocities of the same stars. There were redshift stars caused by the Doppler effect. The farther stars had larger redshifts. They were receding faster. The results were identical to Paul's and agreed with equations 1, 2, and 3. Paul and Peter didn't know why the farther stars had faster velocities. They postulated the existence of dark energy matter with a repulsive force, pushing stars' galaxies to increase their velocities. The stars that astronomers Paul and Peter observed, measured, and read are in our Milky Way: star Xena, which we call Alnitak on the Orion arm; star Human, which we call Burfock on the Perseus arm. Figure 2 shows their locations and relations. We assume our analysis and the astronomers' measurements were made at the same time and not 400 million years apart. Both stars belong to two binary star systems, according to our astrophysicists. The binary star Burfock's center of gravity was farther from the Milky Way center than the system Alnitak. The arc lengths of the gravity center of the system Alnitak orbiting the Milky Way's center were a 1, a 2, a 3, and a 4 for years. 1, 2, 3, and 4, respectively. Burfock's gravity center orbited the Milky Way center at arc lengths B1, B2, B3, and B4, corresponding to years 1, 2, 3, and 4. The distances were A and B for system Alnitak's center of gravity and system Burfock's center of gravity from the center of the Milky Way, respectively. Burfock's elliptical orbit was larger than Alnitak's elliptical orbit. During years 1, 2, 3, and 4, Alnitak orbited its center of gravity at arc lengths of a 1, a 2, a 3, and a 4, respectively. For years 1, 2, 3, and 4, Burfock orbited its center of gravity at arc lengths of B1, B2, B3, and B4, respectively. The arc lengths were A1 less than A2 less than A3 less than A4, much less than B1 less than B2 less than B3 less than B4. The arc lengths of the gravity centers were A1 less than A, 2 less than A, 3 less than A, 4 much less than B, 1 less than B, 2 less than B, 3 less than B4. After 4 years of observation and measurements, our astrophysicists calculated the results in below. Astrophysicists compared the results and measurements. They found out that the astronomers' increased distances of Xena, x1, x2, x3, and x4 were the same as the arc lengths, a 1 plus a 1, a 2 plus a 2, a 3 plus a 3, and a 4 plus a 4, of Alnitak's orbits, respectively. The increased distances of human y1, y2, y3, and y4 were the same as the arc lengths, b1 plus b1, b2 plus b2, b3 plus b3, and b4 plus b4, of the star Burfock's orbits, respectively. There's no mystery about farther stars having faster velocities. The mystery is that astronomers Paul and Peter didn't know the star's orbits and orbit plane angles. A simple example, Jack measured his brother Joe's locations at points A, B, and C, assuming Jack was far away. He didn't realize Joe was riding a Ferris wheel with a 100-foot diameter. Jack was 1,050 feet from point B, which was the same height as Jack's eye level. Jack and the rotating Ferris wheel were in the same plane, figure 8. At the beginning, the distance OA was the square root of 1,000 x 1,000 plus 50 x 50 feet, or 1,001.24 feet. 1 minute later, the distance OB was 1,050 feet. 2 minutes later, the distance OC was the square root of 1,100 times 1,100 plus 50 times 50 feet, 1,101.13 feet. Jack calculated in the first minute that Joe moved from point A to point B. Joe moved at a velocity of 1,050 minus 1,001.24 feet per minute equals 48.76 feet per minute. In the second minute, Joe moved from point B to point C at a velocity of 1,101.13 minus 1,050 feet per minute equals 51.13 feet per minute. At the same time, Jack's friend Jess used the Doppler radar to measure Joe's velocity. For 2 minutes, he read the radar every 10 seconds. His results were the same as Jack's. Joe moved away from them faster. Jack and Jess reported that Joe was driving a car and accelerating away from them. The Ferris wheel takes 4 minutes to orbit its center. The galaxy takes millions of years to orbit its center. Most astrophysicists agree with the perfect cosmological principle that states the universe is homogeneous and isotropic in space and time. When we observe, measure, and analyze the velocities of stars or galaxies 400 million light-years away of used Doppler radar, we compare our results with those of astronomers who live on a planet 400 million light-years away. They read, measure, and analyze the stars or galaxies in our Milky Way, or the galaxies next to the Milky Way measurements, and results should be similar. Both results will state that stars or galaxies are moving faster at an increased distance. However, we know the stars in the Milky Way and Milky Way neighboring galaxies aren't receding. Measurement results or Doppler radar readings contradict this fact. Actually, galaxies orbit massive objects. Lesson 3. Universe is in a stable state. Earth is one of the planets orbiting around the Sun. Everything in the solar system is bound by gravitational forces. When we treat the solar system as one object, it will be one of millions or billions of stars or star systems and small satellite galaxies orbiting around the gravity center of the Milky Way. Figure 3. Everything inside the Milky Way is bound by gravitational forces except a few supernovae or collisions of stars that have the forces or energy to escape. When we treat our Milky Way as one object, Newton's first law of inertia predicts that it will not be at rest or moving at a constant speed in a straight line. It will be affected by supernovae or star collisions that leave other galaxies and hit the Milky Way. Newton's third law states that the Milky Way must move and change direction. External or internal forces change the Milky Way's direction repeatedly. Eventually, it'd attract to the center of the universe and orbit around it, Figure 4a, or it'd attract a massive object-trotter black hole and orbit around it. It'd be one of millions or billions of galaxies or binary galaxies and stars orbiting around a gravity center to form a mass galaxy group, Figure 4b. Everything inside the mass galaxy group is bound by gravitational forces. When we treat the MGG as one object, it'll be one of millions or billions of MGGs, stars and galaxies, orbiting around the center of the universe, Figure 5. Everything inside the universe is bound by gravitational forces. The question is, does our universe exist alone, or is it just one of millions or billions of universes orbiting around a common gravity center? This is to form a mass universe group. Astronomers reported Doppler radar readings indicate that a farther distant galaxy from Earth will recede faster. A galaxy that is 2 billion light-years away recedes faster than a galaxy that is 1 billion light-years away. We know the light we observed from a galaxy 2 billion light-years away was 2 billion years ago. The light from 1 billion light-years away was 1 billion years ago. In Figure 6b, when astronomers measure the light of a galaxy at r billion light-years away, the galaxy must be on the circumference of the circle. If r is 5 billion light-years, the galaxy must be at point A, which was 9 billion years after the Big Bang. It couldn't be at point B, which was 10 billion years after the BB. The light at that point could only arrive at point D, which was 1 billion light-years away from Earth, point E. The light at point C will arrive at Earth, point E, 19 billion years after the BB. Similarly, for r equals 2 billion light-years away, the galaxy must be at a location 12 billion years after the BB, respectively. When we measured the velocities of galaxies 2 billion, 3 billion, and 5 billion light-years away, we got the velocities v2, v3, and v5, respectively. Stars galaxies farther away have faster velocities. We have v5 greater than v3 greater than v2, eq 4. Galaxies 2, 3, and 5 billion light-years away were located 12, 11, and 9 billion years after the Big Bang. v2, v3, and v5 were the velocities of the stars-star galaxies at times 12, 11, and 9 billion years after the Big Bang, respectively. Equal 4 indicates that galaxies' velocities slowed down from 9 billion to 11 billion to 12 billion years after the Big Bang. The universe is not receding faster. Exactly, equator 4 indicates that the universe's expansion has decreased. Eventually, it will come to an end. It was 12.5 billion years after the Big Bang. The universe has reached a stable stage. The expansion has been stopped. As the universe expands, it must start at its center. Galaxies farther from the center move faster. The universe should look like Figure 1a. It expanded from ellipse A to ellipses B and C. That was what happened after the Big Bang, Figure 6a. However, it stopped 12.5 billion years after the BB. We are far from the universe's center, but the Milky Way and its neighboring galaxies don't move away. If we use Earth as the center of expansion, galaxies farther away will travel faster. The universe will look like Figure 1b, and it contradicts our observations. Does the expanding universe theory hold up? It's clear that a gravitationally bound universe has been reached. We used Earth as a center to measure and obtain the velocities of planet Uranus Viv P, Bernard's star Vs, the galaxy N, G, which was 400 million light-years away. Respectively, all had receding velocities. Does it mean they are moving away from Earth? No, they are not. Locating their gravity centers, we will have their actual velocities, speeds. Case 1, the velocity of planet Uranus 5P. We know the location relationships of Earth and Uranus with the gravity center of the Sun. We know both planets revolve around the Sun. Earth has a faster orbit speed. The result is a false indication that observation is receding. Planet Uranus doesn't recede from Earth. Case 2, the velocity of Bernard's star, Vs. This study determines the location relationship between Earth, Bernard's star, and the Milky Way center. The Milky Way center is the gravity center of Bernard's star and the Sun. The Sun is Earth's gravity center, figure 7, in cyan color. Assuming the Sun and Bernard's star have the same orbit speed or a small difference, the velocity of Bernard's star, Vs, is the observer's velocity. It's the speed at which Earth orbits the Sun. The Bernard star doesn't recede from Earth. Case 3, the velocity of galaxy N, Vg. Similarly to Case 2, we use the same figure 7 in yellow color. This study determines the location relationship between Earth, galaxy N, and the universe center. The universe center is the gravity center of galaxy N, and the Milky Way center. We use the figure 4b model. The MWC is the Sun's gravity center. The Sun is the Earth's gravity center. Assuming the galaxy N and the MWC are in the same MGG and have the same orbit speed or a small difference, the velocity of the galaxy N, Vg, is the observer's velocity. It's the Earth's orbital speed around the Sun and the Sun's orbital speed around the MWC. If the galaxy N is outside the Milky Way center's MGG, the velocity Vg is the Earth orbit speed and the Sun orbit speed plus the MWC's orbit speed, or the Hubble constant. The Hubble constant is not the galaxy's receding velocity. The Hubble constant is not the universe's expansion rate. The galaxy is not receding. The universe is not expanding. The universe is bound by gravitational forces. The Hubble constant is the Milky Way's orbit speed around the UC/MGG's center. The Milky Way or galaxy orbits a massive object UUC black hole. Conclusion. When we look at the sky, the locations of the stars inside the Milky Way change slightly in our lifetimes. The reason is that the stars and the Sun orbit the Milky Way's gravity center at slightly different speeds. The Milky Way is gravitationally bound. However, we observe that the stars outside the Milky Way have fast receding velocities. In reality, they are moving at the speed of their orbits. Those stars are inside another galaxy and orbit their center. The star system is magnified to the level of the galaxy. We observe the Milky Way and its neighboring galaxies. This is like stars inside the Milky Way. The Milky Way and its neighboring galaxies' locations change slightly in our lifetimes. The reason is that they are bound by gravitational forces, but they're not attracted to each other. Binary galaxies will form if the Milky Way is gravitationally attracted to Andromeda or another galaxy. However, astronomers living 400 million light-years away obtained that the Milky Way had a fast receding velocity. In contrast, we cannot find any evidence of a receding velocity. It's clear that the Milky Way and neighboring galaxies orbit a common gravity center and form a MGG, figure 4b. Actually, the receding velocity was the orbit speed. The MGG is gravitationally bound. Similarly, we observed that galaxies 400 million light-years away had fast receding velocities, a perfect cosmological principle. They were actually orbital speeds. Galaxies 400 million light-years away are contained within another MGG. Within the same MGG, it is difficult to observe an orbital speed, but outside it is easy. The old universe structure model. The universe has millions or billions of galaxies that do not orbit any massive object. The galaxy has millions or billions of stars as star systems. The star-star system has planets. Based on this model, astronomical observations, measurements, and calculation results that are accurate within the Milky Way but outside the Milky Way will be ambiguous, inaccurate, and incomplete. It misleads us that the universe is expanding faster. The stars, galaxies will have velocities faster than light speed. There is dark energy, dark matter in the universe. Comparison of the observations with those of astronomers living 400 million light-years away. We know galaxies orbit massive objects and are gravitationally bound to their centers. By adding the MGGs to the model, all astronomy observations, measurements, and calculations are straightforward. Equation 4 indicates that the universe's expansion has decreased. Eventually, it will come to an end. A gravitationally bound universe formed 12.5 billion years after the Big Bang.